Very happy to have Aaron Zimmerman today with us. So Aaron is a physicist. He received his PhD in 2013 from Caltech, and he's now on the faculty at the University of Texas, Austin. He's worked on various topics in black hole perturbation theory, numerical relativity, gravitational wave data analysis, and he's also the co-chair of the parameter estimation working group at LIGO. So today he's going to tell us about testing the nature of black holes towards precision ring-down tests. Take it away, Aaron.
Thank you very much, Achilleus. Thank you, everyone, for being here, and thanks for the invitation. It's really great to be here, if only virtually, and I do hope that maybe one day I can actually meet many or all of you. I know some of you previously, but many of you are new for me. So I'll jump right in. And before I jump right in, I should take a moment to mention that I'm a member of the LIGO Scientific Collaboration, as Achilleus mentioned, and today's talk is not on behalf of the LIGO Scientific and Virgo Collaboration. Since this is a colloquium and meant to be towards a broad audience, of course, as usual, much of the talk is going to be introductory in nature, which means I'll be reporting on work I have not done. And so any mistakes I make in describing that work are my own mistakes. Towards the end, time permitting, I would like to tell you about an exciting program I and my student are working on to develop a more precision approach to testing the nature of black holes. But first, I'm going to be presenting the work of other people. So with that caveat out of the way, let me give you just a few words of motivation familiar for everyone at the Black Hole Initiative. The main motivation is this remarkable fact that black holes have no hair, at least from the classical solution of Einstein's field equations. The black hole solutions that we find are the simplest objects we know of in classical physics. They can be described by two properties and only two properties, their mass and their spin, S. And I'll be using throughout this talk instead the dimensionless spin parameter, which I'll label as chi. This is a dimensionless number between 0 and 1 for black holes. If it goes above 1, the black hole would lose its event horizon and be a naked singularity. And we don't think that that is a physically reasonable solution. Given the mass and the spin of a black hole, we know all about all of its higher multipole moments. And I should add that while I'm focusing on mass and spin, it is true that black holes can have other kinds of conserved charges. And so they can have more than just these two quote unquote hairs. But when we think about astrophysical black holes, those we might be able to study and probe in our own universe, we expect these charges to be 0. In particular, electromagnetically charged black holes will tend to neutralize themselves by drawing in charges from the external environment, or even by creating pairs of positrons and electrons in the very strong potentials outside the horizons of a black hole that's been charged to any significant level. So in point of fact, black holes we expect to see in nature are going to be uncharged and just described by these two parameters. But quantum field theory on curved spacetime, black hole thermodynamics, theories of quantum gravity, they all point very clearly to the idea that, in fact, black holes should have many different possible microstate geometries. In fact, an enormous number of possible microstates could be represented by the macrostate of a black hole. And so already we have some tension. In addition to this, the fact that black holes harbor these singularities leads to a lot of ideas for how one might resolve those singularities. Perhaps quantum effects resolve the singularities. Perhaps black holes that we see in the universe are in fact some kind of exotic compact object where some new physics kicks in to prevent the formation of a horizon and eventually singularity. These are all ideas that we would like to test with data. Finally, even if you don't think that black holes have some kind of interesting microstate structure, and even if you think they really are the black holes of Einstein's theory, black holes can have these other kinds of hair if there are light scalar fields or even vector fields in the universe with the right range of masses. It turns out that there is an instability. Black holes can produce, through a superradiant instability, a cloud of these particles around them, which in turn sort of dresses the black hole with more information. And so you might think of this as a sort of superradiant hair that the black hole might have. Well, when it comes to testing the nature of a black hole, finding out if black holes really have no hairs, gravitational waves from binary black hole mergers is really an unprecedented opportunity for us to run these tests. Here I have depicted for you the typical gravitational wave signal coming from the in-spiral and merger of two black holes. They all follow this sort of characteristic pattern. There's a long in-spiral phase where the black holes slowly spiral together and emit waves with an increasing amplitude and frequency. This can be treated using post-Newtonian approximations, approximations perturbative in velocity over the speed of light. Then we enter into a merger regime where really space-time should be considered a dynamical entity in its own right, and only numerical simulations of binary black hole mergers can give us accurate predictions of what happens as these two black holes merge together into a single strongly deformed black hole. And then sometime after that merger, the black holes enter into a final phase called ringdown, which is the focus of this talk. This is an exponentially damped phase of emission where that perturbed black hole relaxes down to its final state with a final burst of emission. The important thing about ringdown is it can also be treated analytically. The way you think about it is you think about the final state black hole, and as you move backward in time, the space-time becomes a successively stronger perturbation about that final state. So you can treat it using linear perturbation theory around that final state up to some point, and I'll get into where that point is as we go on in the talk. So that's the motivation. Let me add that I did aim this talk for just a little over 30 minutes, so please do jump in with questions, or we can take time at the end to discuss whatever is most normal here. And don't hesitate to interrupt. I may not see any questions posted in the chat. So the first part of this talk is just going to be a review of the theory of black hole ringdown. I'm going to need a little bit of quantitative theory on black hole ringdown in order to explain the very end of the talk, the proposed direction in which we can begin to do precision tests of black hole ringdown. So to start with, I think it's good to describe this nice mental model I have, which I think is a useful mental model for how black hole ringdown works. And the way to describe this mental model is to take a step back and imagine we just shine a laser beam at a black hole. Qualitatively, two different things could happen when I shine a laser beam at a black hole. Either the impact parameter of that laser beam is large enough that the laser beam just gets bent by the strong gravitational curvature of the space-time, and then continues off merrily back to large distances. Or, of course, the light beam can be absorbed by the black hole. You can imagine that if you tune the impact parameter here, there must be some transition between these two extremes. And indeed, there is an unstable orbit, a place where if I tune that laser beam just so, it can go onto an orbit forever, trapped between these two states. This is a very finely tuned solution, and any small perturbation will cause that laser light to eventually head off to large distances or be absorbed by the black hole. But this is essentially what ringdown is. Ringdown is not waves being emitted by the black hole itself, of course. Nothing can come out of the black hole horizon. Instead, ringdown occurs because waves of various kinds can be trapped in this trapping region near the black hole, near where these photon orbits exist. And those waves will gradually leak out off of this trapping region and either be absorbed by the black hole or head off to infinity, where they could be detected, for example, by a gravitational wave detector. Now that's one mental model, but dealing with light rays isn't really sufficient when we want to think about wave mechanics on black hole spacetimes. So in order to further understand ringdown in more detail, we need to understand how waves propagate around black holes and look at another mental model for ringdown, which comes out of solving the simple scalar wave equation, but on a curved background. So this is just the classic wave operator, but on a curved spacetime. And the nicest place to start with this discussion is to actually focus not on a spinning black hole spacetime, but on Schwarzschild, non-spinning black hole, which is spherically symmetric. That spacetime has a time symmetry and is symmetric to all rotations. And so we know that I can solve this equation by separation of variables, decomposing the scalar field into frequency harmonics because of the time symmetry and spherical harmonics because of the angular symmetry. And we are guaranteed that if I plug this ansatz into the wave equation, the whole problem will reduce to solving a single ODE for the radial wave function, for a radial part of the wave function. And this equation now should look very familiar from just elementary quantum mechanics. We have some potential, which is presented by the region where that photon orbit is. And we have waves with frequency omega, which are going to scatter off that potential. Okay, so our laser beam's now been replaced by an incoming wave. As it approaches this region near the black hole, it can be partially reflected from that potential or partially transmitted and eventually be absorbed by the black hole. And by studying this radial wave equation, just as in elementary quantum mechanics, we can calculate these reflection and transmission coefficients. Now, just like the case with the light beam, we can imagine what happens if I carefully tune the frequencies involved here and try instead to demand not that I send a wave in, but that I only get waves out. I'm going to fix my boundary conditions so that instead of having to scatter a wave off the black hole, I just have waves coming out of this strong field region, heading off to infinity or down into the horizon. This is the case where I have waves that are leaking out of that trapping region. And just as in the case of the laser beam, only certain tuned frequencies will permit this to happen. But you can solve for those frequencies. You discover that there's a whole hierarchy of different omega LMNs. These are eigenvalues of that ordinary differential equation indexed by their angular quantum numbers and by an overtone number I'll discuss in a little while. And they sit in the negative imaginary half of the complex plane, which means that they represent decaying oscillations. I like to remember also at this point that these frequencies, these poles, these frequencies of these modes of the wave equation should be thought of as poles in the green function, poles in the propagator that govern wave propagation in a black hole spacetime. I think it's good to be reminded of that because it tells you how to create the ring down. Essentially, any initial data whatsoever, or any source which emits waves over some range of frequencies, when you convolve that source or that initial data with the green function to get the waves coming out of the spacetime, these poles will be excited by the residue theorem and will cause some component of the outcoming wave to be oscillating at a particular real part of the frequency and decaying depending on the imaginary part of the frequency. All right, that's the warm-up, scalar waves on Schwarzschild. We want to now go on to spinning black holes, to the Kerr solution. In this case, we start with the scalar wave equation. We're lucky. Again, you can apply separation of variables. It's not obvious that this would happen, okay? A Kerr spacetime has a time symmetry and an axial symmetry, but no other obvious symmetries. And so therefore, it's not obvious that you would get a full separation between radial and polar components, but it does happen. On the other hand, if you study the linearized Einstein equations around Kerr, the metric perturbations, if I imagine starting some gravitational waves on that spacetime and letting them evolve, those perturbations don't separate. And that means that it's difficult to do this analysis and discover the quasinaural modes and the quasinaural mode frequencies that make up Ringdown. But by some miracle, in fact, it turns out that you can address this problem and you can get separable wave equations. In 1973, Tucholsky published a paper showing that if you focus on certain other kinds of scalars, you can get separated wave equations. The idea is that for scalar waves, electromagnetic waves, or even gravitational waves, if you focus on curvature quantities, you can then project them using a special basis of vectors that are natural to the Kerr spacetime into complex scalar quantities. Okay, these are essentially just components of these tensors in a specific basis. But these special components themselves, if you analyze their evolution, obey a single master wave equation, a wave operator on a scalar, which is indexed by its spin weight s. S equals 0 scalar fields, plus minus 1 is electromagnetic, plus minus 2 would be gravitational. And this master wave equation does admit separation. And so you can separate it out. You can arrive at an ordinary differential equation for the radial wave function, and you can once again solve for the characteristic frequencies of Ringdown. There's a straightforward algorithm for doing this called Lever's algorithm, which was introduced by Lever in the 80s. It's a very accurate and straightforward way of calculating these frequencies. And so with this algorithm and this formalism in hand, we can actually calculate as a function of spin of the black hole, the entire spectrum of oscillations of a black hole spacetime. We discover that we have a sequence of modes indexed by their angular quantum number. And as we dial up the spin, we get a magnetic splitting of these frequencies, just like if you put a hydrogen atom in a magnetic field with the strength of the splitting depending on the size of the spin. Now, the mass overall sets the frequency scale. This is because black holes have no intrinsic scale, right? I can make the black hole more or less massive, rescale all distances by that mass, and I get the same solution. So the total mass of the actual astrophysical black hole sets the overall scale of these oscillations, and that's roughly 16 kilohertz for a solar mass black hole. Fairly high frequency when we think about ground-based gravitational wave detectors. What we see is that as we increase the spin of the black hole, roughly speaking, the frequencies go higher. And also as we increase the spin of the black hole, the damping time also goes up, meaning the oscillations last longer. The quality factor of these oscillators goes up. But if we take a bigger step back, these quality factors are pretty crummy, around 2 for the modes of interest. This means that you only really get a couple oscillations out of your ring down before it's decayed away significantly. And that means that ring down's quite hard to measure. However, by thinking about the spectrum now, we see a really beautiful and clean test for the nature of black holes that we can generate using ring down. If we can measure just a single mode of this ring down, a single damped oscillator, we can get the mass and the spin from the frequency and decay time of that oscillation. And if I can measure even a single other mode, then I have a clean consistency test. That single other mode had better be consistent with these predictions at that mass and spin, or else this is not a Kerr black hole. So that's a very compelling story. It's a very clean test of the nature of a black hole spacetime. And now that we're in the era of gravitational wave astronomy, we can imagine carrying this out, and it has been carried out. And I'm going to spend part of the rest of the talk describing those measurements. So let's look at measuring ring down now. Now, originally, before the very first detection of gravitational waves, it was thought that these kinds of ring down tests of a Kerr spacetime would actually have to wait to the far future. They might require third generation ground-based or even space-based gravitational wave detectors. And this diagram illustrates why. The red curve is the amplitude spectral noise in the very first observational run by advanced LIGO. And the blue curve is the design sensitivity. These measure the sensitivity at different frequencies of these detectors. And this blue trace is a fiducial signal for a 10 solar mass black hole in spiral merger ring down. Now that merger ring down portion happens right here, well below the sensitivity of the early parts of advanced LIGO's observational campaigns, and even pretty low compared to the eventual hoped design sensitivity of advanced LIGO. On top of that, this is a pretty small part of the overall signal. The ring down doesn't last very long. So with these things combined, it was believed that there really wouldn't be enough signal to noise to do any clean measurements of ring down. But nature was kind to us and gave us some hope, because in fact, the very first gravitational wave looked a little bit more like this. It was the merger of black holes around 30 solar masses apiece. Their merger ring down happened right in the middle of LIGO's sensitive band. And indeed, if you look at the raw data, bandpass filtered into the sensitive, into the most sensitive regime of LIGO for this very first detection of gravitational waves, and you squint really hard and you lie to yourself just a little bit, you can imagine that, yeah, I see the ring down, I see it right there. Well, of course, you need to actually use the correct data analysis techniques to see if there's a ring down. And this was carried out on that very first signal. But this testing ring down now forces you to confront this question. After merger, we have this very perturbed object. So how long do I have to wait after merger before the perturbation theory prediction is good enough to work? And so in order to address that question experimentally, what the LIGO and Virgo collaborations did for this first merger is that they took the merger time, estimated from a full analysis of the waveform, and they started to fit the signal to a single damped sinusoid, just one ring down mode, starting at some time after merger, and then fitting forward. And they extracted the inferred frequency and decay time for that mode. What I'm plotting here are actually something I'll plot for every LIGO observation, LIGO Virgo observation. These are actually posterior probability densities. Okay, so when we make inferences on a gravitational wave signal, our actual final measurements come in the form of probabilities over the inferred parameters. And we will generally plot for you these contours, which contain 90% of the probability. Okay, there's more information in our analysis, for example, the place where the signal is most likely to be, but these 90% give you a good idea of where to expect the parameters to be. Now, what happens when you start this analysis only a millisecond after merger? Well, you get a lot of data, and so your measurement is tight, but it's biased. That's because in the beginning of the ring down, there may be other ring down modes active, and maybe also linear perturbation theory isn't good enough. But if you wait too long, you don't have enough signal and your uncertainty contours are gigantic. There's a sweet spot in between at about 5 milliseconds where you get fairly tight contours, and they're centered right over where a full, complete analysis of the whole signal would predict these frequencies should be. So this is not a ringdown test of, this is not a test of ringdown. This is not a test of the current nature. This is a consistency test overall of the entire waveform model and a very first measurement of just one mode. Remember, we need 2 modes in order to make a clean ringdown only test of the nature of a black hole. So what comes next? Well, you might, yeah, please.
So you said there's uncertainty about where to begin measuring the ringdown.
Yes.
Is there no uncertainty about where merger happens?
So that's a good question. Here, that merger is just a parameter of the waveform models themselves. So in some sense, you can actually define a particular point in a given model as the time of merger, but you're completely right. Due to the uncertainties in all of our measurements, this time of merger is actually a fuzzy thing, even if I define it as being a particular moment predicted by the waveform model, because many waveform models fit the signal. So already this is fuzzy. So you're totally right. You have to choose a fiducial value and proceed. Now that shouldn't be satisfying, and it's not satisfying, right? This is a process where we're continuing to improve. And what I'd like to tell you about next is one way to start to improve on this procedure. But are there any other questions before I move forward? Okay. Again, please don't hesitate to chime in. And as usual, if you're getting lost or tuning out a little bit, the best way to fight that is to ask any questions. So how could we make this a better analysis? Well, for one thing, we'd love to not lose all that data at the beginning of the ringdown. And we can, in fact, push earlier if we consider this idea of overtones. So this is another plot of the quasi-normal mode spectrum in the complex plane due to Lever. And what you see here is that for a fixed angular harmonic, there's actually a whole sequence of ringdown modes. Okay, what these modes are these are the higher overtones at a fixed angular harmonic. Okay, these aren't classic higher overtones in the sense of music. They happen not necessarily at higher frequencies, but instead what they do is they happen at higher decay rates or longer or shorter damping time. So these modes damp away much faster than what we call the n equals 0, the fundamental mode in a given angular harmonic. Now, what Lever showed is that if one wants to fit the ringdown that happens after you throw something into a black hole, just using the predictions of perturbation theory, if you just use the lowest overtone, you get a good fit to the end of the waveform where only that least damp mode is still surviving. But if you push it further and include ever more overtones, you can push the goodness of this fit to earlier and earlier times, even up to close to the moment where, say, a particle plunges into a black hole. And so perhaps by including more overtones, we can do better. And this was carried out by Giesler, Issy, Schiele, and Tucholsky. They revisited this idea using numerical simulations. There's a lot going on in this plot, so I'll try to explain it piece by piece. What's being plotted here is the match between a model for ringdown, which incorporates some number n of overtones, either just the fundamental mode or the first, second, third, and so on overtones. This match to the data is computed starting at a given time, t0. Okay, so the idea would be at, say, 20 times m after the merger, you fit forward from there and you achieve this good of a match. And the earlier you go, the worse your match. That's natural because the quasi-normal modes fit best late in the ringdown. What they showed is that as you steadily increase the number of overtones you use in your fit, you can keep a good fit all the way up to the moment of merger in the simulations. Now, on the one hand, this is perhaps expected because you're including more free fit parameters. You expect to get a better fit, but they did perform a large number of consistency tests to try to demonstrate that, in fact, this improvement is happening because these overtones are really in the data. And if you use these overtones in your signal, you can really fit all the way up to the moment of merger. That's a really remarkable thing. And it's something that I think we still need to understand theoretically. But using this idea that more overtones can improve the observations, they went ahead and reanalyzed GW 150914 in this other paper. Now, the problem with doing a ringdown test is that to really make a good test, you'd have to let every frequency in your model float and let the data tell you what those frequencies should be. There's just not enough information in the data to do that accurately. So instead, what they did here is sort of a consistency test. They said, let me use no overtones, one overtone, or two overtones, and let me always fit starting at the moment of merger. But these overtones are going to be as predicted by general relativity for a given mass and spin of a black hole. They will only fit using the Ringdown portion of the signal. And then they used that Ringdown signal to infer just two things from the data, the mass and spin of that black hole. So remember, you can measure that mass and spin from one mode, but here they're using the extra modes just to increase the range over which they can use the data from the Ringdown in that measurement. And you can see that for no modes, they get a very biased measurement because things are biased by the other overtones. But at 1 and 2 modes, they achieve a fairly good measurement consistent with the full analysis. Again, this is not yet a no-hair test using Ringdown only, but it's pointing the way. It says that if we could incorporate these overtones, we can get sharper measurements on our data and do the very best we can.
Another quick question.
Yeah.
So you often hear people make statements which I have never been able to verify, in a way that's satisfying. But you often hear people sort of claim that the entire set of quasi-normal modes is a complete basis. So you should, in principle, be able to get the entire signal, not just post-merger, but if you include enough QNMs.
I don't know who's claiming that because it's not true.
Not true.
So in fact, so this is a little bit of an aside. So what does black hole perturbation theory tell you? Let me rush back in time a little bit to my green function picture. Actually, in addition to the poles, there is also a branch cut in the propagator, which leads to another kind of late time signal, not just a decaying exponential, but actually a power law decay. These are known as the tail emission. So on top of the quasi-neural modes, there is also a tail emission expected. So there's simply no way to get that tail out of the modes. And so it's not possible to do everything with the modes. On the other hand, these tails, we know from numerical studies, are very weak. And so we don't have to worry about them at the level of today's observations. Now, there's a different concern, which is this idea of fitting using damped sinusoids. When you fit using damped sinusoids, people sometimes use the words overcomplete for that basis of damped sinusoids. That's just the idea that you can fit anything at all with damped sinusoids, even something that's not really a damped sinusoid, by playing with the amplitudes and phases. You can even get a signal which grows in time, not shrinks in time, by playing with the relative phases and amplitudes. And so a classic barrier to these kinds of studies in the past has been the lore that the damped sinusoids are an overcomplete basis for fitting purposes, and therefore these kinds of things are artifacts of fitting. They're not real physical things. This is not really extracting information from the Ringdown, it's overfitting. Like I said, they tried to do a lot of consistency tests to try to fight against this notion. And in practice, so far, what's worked well in observations is using just a single additional overtone, which I think is completely reasonable. So I don't know if that fully addresses your question, but that's at least two aspects of it.
Yeah, the first aspect about the tail, that is thought to be relevant for even later times, right?
Yes.
Post Ringdown.
Yeah, exactly. So basically the idea is that in any reasonable excitation process, the tails get excited to a very low level. But on the other hand, they're a power law decay in time. So they decay slower than an exponential. And so eventually all of the quasi-neural modes decay down so low that the only thing left would be the tails. Now, to actually extract those tails from numerics requires some effort. And to extract them from data is something I don't think anyone has attempted, and I don't think is feasible anytime soon. But an interesting idea. Okay, so with the stage set in terms of measurements of Ringdown, with one, and this is only one method of doing this, by the way, I'll talk about another one in a minute, but with a good method set, we can now turn to the data as it stands. This is the current catalog, GWTC2, of all candidate events detected by the LIGO-Virgo collaborations in gravitational waves. It comprises of 50 events. 47 are binary black holes, 2 are binary neutron stars, And one is perhaps a neutron star black hole, probably a very high mass ratio black hole binary. And as we confront ourselves with this huge data set, some natural questions arise. First of all, maybe one of these events will be nice and strong in its ring down, and we'll be able to do a consistency test with just that. But that doesn't seem very likely. So instead, you can ask, how could I use all of these observations and combine them together to test the Kerr hypothesis using ring down? And that's what we'll turn to now. So before we get there, I need to mention just one quick word about how tests of GR are generally carried out by the LIGO collaboration. They're primarily null tests. The idea here is we have some prediction for what our signal should be given by general relativity. Here, a sum over different decaying sinusoids with these modes given by GR. And then you might pick one of those parameters and you might perturb it with a free parameter, delta. And then you would add this to your model and you would constrain this extra parameter. Okay, if this extra parameter is within uncertainties consistent with 0, you declare victory for GR. If it's inconsistent with 0 within the uncertainties, you have a signature perhaps that something is going wrong. Now the problem is that these null tests are great on an individual event by individual event basis. If one event really violates GR, you can measure it, you can see it in these parameters, and you don't need to know what caused the deviation. Okay, these are agnostic tests. But the problem comes in when we try to bring all of our events together. And there we have to do something else. So how do we combine multiple constraints? Well, we discussed this in a paper. We discussed 2 different ways forward in a paper and provided this example for the problem of using null tests and combining them together across multiple events. So this is a toy model of what the gravitational wave signals would be like if the graviton had some mass, some quantum wavelength lambda g. The effect of that is to perturb a particular parameter called P2. Details are not important, but it's the first post-Newtonian parameter in the in-spiral part of the model, and it will cause some deviation, which you can predict from a model with a massive graviton. And if you were to make a bunch of measurements of this deviation parameter on synthetic data, you would get a whole host of different deviations, none consistent with each other. And if you were to try to combine these consistently, you might end up saying, oh, there's no deviation from GR at all because these are not consistent with each other. Now, clearly what you really need to do is you need to figure out that they're all coming from a particular beyond general relativity model, massive graviton, translate these constraints into constraints on the Compton wavelength of the graviton, and now they all sit consistently on each other. And you could then combine all of these to derive a very sharp measurement of that parameter. So either you need a specific theory to combine these tests across multiple events, or you use what's called a hierarchical analysis, which we also suggest in this paper. That's basically the idea that you'd no longer assume that all the deviation parameters come from, all the deviation parameters have to be the same from event to event, but instead you assume they come from a distribution and you measure the properties of that distribution. And in particular, you can assume that the deviation parameters come from a Gaussian centered on some mean. And if it's general relativity, that's the true theory, that mean is 0 because the deviations overall should always be scattered around 0. And so this hierarchical analysis was first carried out by some colleagues of mine on the 0102 data and has since been adopted by the LIGO Virgo collaborations for all of the observations in the 3rd observing run, including the ones I'm about to tell you about now. So given that I'm already pretty far into the talk, I think this will be close to the end before I take time for questions. But let me just tell you about where things stand in terms of ring-down tests from O3A, the first half, that's A, of the 3rd observing run, the one which gave us 39 new signals. An analysis of these was published here using many, many different kinds of tests of GR, including ring-down only tests. And so the first test I'll show you the results of, called PyRing, is a ring-down only test using those overtones, like I mentioned before. So how does this work? You use a 2-mode model for the ring down. The fundamental mode, n equals 0, and the first overtone, n equals 1. The fundamental mode you use to measure the mass and spin of the final black hole. That gives you then a GR prediction for the first overtone, but you allow that first overtone to float. And you see if this deviation in that first overtone is consistent with 0 or not. And that's what you're seeing here. The posterior distributions for a few selected events for how the first overtone deviates. This is in some sense a true Ringdown no-hair test. It uses two different modes and combines them together to do a consistent check on general relativity. You can see here the very first detection, GW 150914, it's 90% contours. You can see two other events where the evidence for having a overtone present in the data was large enough that we think there's an overtone present in the data. Those are also plotted. And then there's a combination of 17 events where there was any evidence for ringdown whatsoever in the data. Remember, for very low mass systems, we might not have any observation of ringdown at all. For higher mass black holes, we get a better measurement of ringdown. And that hierarchical combination, we see that it constrains the first overtone's frequency to be well within a limit prescribed by GR, but we don't actually get hardly any constraining power over the decay time. So this is it. This dashed curve is the result of all that we know so far and a sophisticated model. And you can see that we're still in the early days. This is almost a 50% on the overall level of that frequency, a 50% uncertainty. But this analysis can be continued as we get more signals. Another kind of analysis was presented, which allows us to use the full ringdown in a different way. The idea here is that one uses the entire waveform. So a full consistent waveform model, which includes the in spiral, that merger phase, and the ringdown, but it allows the ringdown to vary and then measures those deviations from the ringdown. By bringing information from the in spiral and merger, one informs the ringdown better. And so instead of having to add more overtones to get a measurement of these deviations, one gets that information from the earlier parts of the signal. Plotted here are the only three events where there was a signal to noise of greater than 8 in both the ringdown portion and the in spiral merger portion. So these are the only events where this test is expected to be really sharp. And you can see the 90% contours here, all consistent with general relativity, except maybe very marginally this particular event. They all have area codes now. So, you know, it's gone are the days where we knew each event by some cool nickname. Now they're just a string of characters. But again, if you hierarchically combine these all together, the combination is fully consistent with general relativity. So that is where things stand today. As we look forward, what I wanted to present to you was some new work I'm doing with a graduate student to go towards precision tests of ringdown. And I'll talk about this, if time permits, at the end of the questions for anyone that's interested. But let me just go through the rough idea. The rough idea is that we want to now, to do the most precision test possible, we want to now do this idea, where instead of using the deviation parameters, we choose a specific theory, take those deviation parameters, map them to a measurement of some theory parameter, and then we can combine naively many, many events all together to get sharp measurements or constraints on these alternative theories of gravity or alternative models for Kerr black holes. The only way to do that, though, is to be able to predict quasi-neural modes in black hole spacetimes that are not quite Kerr, black hole spacetimes that are a little bit different than Kerr. There's been a lot of work on this already. Some examples, and this is not even close to exhaustive, some recent examples are here, to develop very general frameworks for computing how the quasi-neural mode frequencies shift when you change the black hole background, but they all focus on expanding in small spin. Meanwhile, merged black holes have spins that are expected to be fairly close, well, not that close, but fairly large, about 70% of maximum, which means that it might be good to instead have an approach which can compute these quasi-neural mode shifts, but for rapidly rotating black holes. The way we do this is to leverage some old work that I worked on while I was in graduate school to map that problem onto an eigenvalue perturbation problem, exactly the same as in quantum mechanics. I'm not going to go over these slides. Again, I can talk about them after questions. Let me just tell you that there's a straightforward way to do this and to compute the shifts in the quasi-neural modes when you know how you've transformed your space-time away from Kerr. With a student, Asad Hussein, we've tested this against a particular very popular alternative for Kerr black holes, the Johansen-Psaltis metric, which has been used to study a test of GR using accretion disk physics and observations of supermassive black holes. And we can compute the quasi-neural mode shifts even for extremely large spins, quite easily. The method that we're working on can be extended to cover the gravitational case. And we know how to deal with some of the technical complications that arise in the gravitational case because of past work I've done in the quasi-neural mode shifts in charged black hole spacetimes and studies of the possible onset of transient turbulence near rapidly rotating black holes. And so I think all the technical challenges can be overcome. But in the meantime, I'll just conclude and turn it over to questions by looking ahead. So quasi-neural mode predictions in spacetimes other than Kerr would allow us to leverage the current data analysis techniques with multi-mode ringdowns for precision tests of the nature of Kerr black holes. Our particular method, this eigenvalue perturbation method, is flexible and can be applied to spacetimes even at very high spins. There's just a few technical challenges that we need to overcome, which I think are within our reach. But if we think about observations, this is a plot of the cumulative number of detections in each of the observational campaigns. And this plot just tells you how much total spacetime volume has been probed. So more or less, what really matters is that this is kind of like a detections per time plot. And you can see that in 01, we just had a few detections. In 02, there were some more. In 03, there were even more. But notice that 03A was 6 months, 02 was 6 months. But the number of detections in 03A was about 4 times larger. As the detectors continue to improve, the rate of detections goes up and up and up. And over the next several years, we should expect hundreds of detections of binary black holes. By developing these kinds of methods that allow us to combine optimally many, many detections together, we're going to be able to move into an era of precision tests of ringdown, perhaps even over the next several years. But certainly, when we look ahead to 3rd generation detectors and space-based missions like LISA, we know that there's going to be a huge number of detections. Some of them are going to be extremely high signal and noise. And so these kinds of techniques are also going to be needed to make the kind of precision predictions we will need in order to test the Kerr hypothesis in the decades to come. So I'll conclude there, and thank you very much for your time.
Thank you. Thanks, Aaron. Very nice. So yeah, we have time for questions. Please raise your hand. Kefe is first.
Hi, Aaron. Thanks for the talk. I just have a question about these tests that are being done. Essentially, when you do these tests, do you consider the frame that the final black hole is in at all? Like, do you do anything to map it to the rest frame, or do anything with fixing the BMS frame?
Good. So let me start with the kicks. So of course, the ringdown predictions are generally made assuming a stationary black hole. And so since actual black holes are kicked by the final emission, it's natural that there would be some redshifting of the ringdown signal. However, that's expected to be pretty small in all but the most extreme cases. And at the moment, I don't think that kind of redshifting has been specifically incorporated, although it is basically degenerate with cosmological redshift. And cosmological redshift is incorporated and has to be incorporated into this model, right? So that's the first thing I would say. The finer details about the kick would be that it might induce some kind of interesting mode mixing, but that's very suppressed. And so at the moment, I don't think there's any need to introduce anything about kicks at the moment. That might be something for very precision models later on. In terms of the BMS frame, I think this remains a bit of a question mark. Now, waveform models are generally tuned to numerical simulations. And so whatever BMS frame the waveforms are being extracted from simulations is kind of the frame that waveform models are going to be calibrated to. And so you can imagine transforming things a little bit. But again, I think so long as your frame is relatively close to the center mass frame of the black hole, maybe then incorporating some boost, there's not much to worry about, and that boost effect is small. In terms of the ringdown modeling, again, one just uses an asymptotic frame based around a black hole spacetime. So it's a very simple BMS frame for the analytic theory.
Okay, thank you. Yeah, I'm a numerical relativist with.
No, I know. I know you. It's nice to meet you. I'm in SXS as well, but I don't make it to the meetings often enough. So sorry that we haven't chatted before.
No, got it. Well, thank you again.
All right, Shep is next.
Yeah, nice talk. Thanks. I had a more basic question. One of your first slides, you showed the photon orbit.
Yeah.
And you made an analogy with the fact that many orbits around in the photon orbit can be related to the ringdown.
Yes.
And so I'm trying to understand that a little bit better. How does that analogy work really? Because gravitational waves are not actually orbiting the black hole.
Good.
And the related question is, can separate ways to measure the photon orbit, let's say with radio interferometry or something, gain any traction on the validity of some of the methods you're talking about with Ringdown?
Absolutely. So let me start with the first question, which is, again, this is a bit of a mental model. I think it is a useful mental model, but it is not perfect. However, it can be made mathematically precise. So some of the other work I did, the paper is Yang et al. I used to have it cited here, but I took it off. As a grad student, drew a quantitative connection between these pictures, and the quantitative connection is the high frequency limit. So just like in geometric optics, if you study the propagation of waves at high frequencies relative to a media, you can understand the propagation of those waves just by ray tracing, right? The same is true for any kind of wave in a black hole spacetime. When its frequency is high enough, its wavelength short compared to the curvature scale of spacetime, you have to be able to map those waves onto null rays. And so there is some correspondence between these null orbits and wave phenomena, and that correspondence gets better and better at high frequencies. That correspondence is that a null orbit is some superposition of high frequency quasinaural modes. So it is made more precise in the very high frequency limit, very high angular overtones, very high frequencies. But at the lower angular overtones, like the quadrupolar waves that are the most important waves coming out of these black hole mergers, it is only a qualitative picture that actually helps your intuition a lot. And in fact, if you calculate the frequency of these orbits and you calculate the decay timescale, how these orbits slide off this null orbit, you will get a very good approximation to quasinaural mode frequencies and decay times. Now, your second question was about how could observations of the null photon orbits from radio and other observations help impact this? Absolutely. So if we go back to the JP metric, this metric was designed specifically for disk and radio observations, right? As a alternative to the Kerr spacetime, where you could easily understand the orbits and potentially also the disk and the iron K alpha lines and everything else, but as a function of some deformation parameters, here epsilon3, which should be 0 in Kerr. And so that's just an analogy, but basically the idea is that any tests of the Kerr spacetime arising from observations in radio of disks and so forth are going to be mappable onto quasinaural mode shifts, provided you have a background model. And any deviation in one must map to a deviation in the other.
Okay, thanks a lot. Very
Thanks
nice.
for the question.
Yeah. Any other questions? Perhaps I can follow up quickly on the first question that Shep asked. Can you repeat? So the precise relationship between the two mental models is in the high overtone limit and high L?
Good. Not high overtone, actually. I don't actually know the connection between higher overtones in the geometric optics picture. I think there's something else. I think, for me at least, I don't know if in the literature as a whole, but certainly for me, I'm missing a really good mental model for the high overtones. Instead, we have to think about the high angular harmonics. So these waves come with different angular harmonics, the quadrupolar mode, the octupolar mode, hexadecapolar, and so on, as L is increased. Right. And if we want to concentrate, right, the quasinaural mode into a small region of spacetime, both in terms of radius and in terms of an angular position, and map it onto a given, say, tilted orbit or an equatorial orbit, right, we're going to need a high angular mode number. And so the WKB approximation for quasinaural modes involves simultaneously taking the frequency, let me go back to some slide, I don't know which slide here, simultaneously taking the frequency, omega, to be large, but also taking L to be large at the same time. And in that limit, then you can develop a connection between quasi-neural modes and the geometric optics picture.
And then is there a conjecture about what the discrete overtone number would map to?
Unfortunately, the WKB approximation does a pretty poor job of predicting overtone number. You can get an overtone number out of the WKB approximation, but it comes out of like an even set of levels in some parabolic cylinder function expansion. So I don't know. Instead, I think there is a different set of conjectures about the very high overtone number quasi-neural modes. These were dealt with by other people long ago. I'm going the wrong direction. I apologize for flashing through all these slides. In short, there's other conjectures about those high overtone numbers, which are thought to relate to black hole thermodynamics in various ways. And there are approximation methods expanding in high damping rate that can actually analytically approximate those modes.
Yeah. All right. Any other questions? I don't see any hands raised, but if you have a question, you can just unmute yourself and ask. Going once, going twice. Okay, if there are no more questions, then let's thank Aaron again for a very informative and inspiring talk. Goodbye, everybody. We'll see everyone next week.
Thanks, everyone, for being here and for inviting me. Have a good one.
Yeah. Thanks a lot.
Thank you, Aaron.